Dzień dobry Państwu. Pora rozpocząć nasze spotkanie. Spotkanie będzie się odbywało w języku angielskim. Good evening, ladies and gentlemen. It is time to begin our meeting today, which will be conducted in English. My name is Krzysztof Turzyński. I'm the Deputy Dean for Student Affairs here at the Faculty of Physics, and I'm substituting for Professor Piotr Sułkowski here, the head of the Zapytaj Fizyka, Ask a Physicist lecture series. As always, today we have an absolutely unique guest, Professor Jean-Sébastien Coe, and he works in low-dimensional condensed matter physics at the University of Amsterdam, and he specializes in using non-perturbative methods to highly correlated systems in magnetism, cold atoms, and quantum nanostructures. So let me say a few words about the scientific way that Professor Coe traveled before he got there. He started his studies in Montreal, and then when he received his bachelor degree, and then he moved to Oxford when he graduated with a PhD in 1998. After a postdoc in Vancouver, he returned to Oxford as a member of All Souls College, and in 2003 he became a professor at the University of Amsterdam. He received many prestigious grants, and one that perhaps will tell you the size of Professor Coe's achievements is the ERC Advanced Grants. But in addition to being a scientist, I would say that Professor Coe is a science activist too, and he is very into publishing in open science. He leads a foundation, SciPost, a non-profit foundation that helps people do that. And if you are interested, please check the website scipost.org. Without further ado, I would like to invite Professor Coe on the stage, and let's spend the next 3 quarters about talking and listening about the pursuit of exactness in quantum physics. Professor Coe, the floor is yours.
Okay, thank you very much. It's a real great pleasure for me to be here. It's my second time in Warsaw. The reason I'm here is because Miłosz Panfil used to be my PhD student in Amsterdam, and then collaborations ensuing and carrying on like that. I guess I've got my plug into Warsaw now, which I greatly enjoy. Especially considering that when I landed with the plane last Thursday, I saw some snowflakes falling, and as a Canadian, this warmed my heart very, very much. Unfortunately, the sun and the heat came, but still, I saw some snowflakes, so I was very, very happy. So I have 3/4 of an hour to give you an introductory idea on the ground story behind the research that I'm passionate about and that I'm trying to push forward. So the title is The Pursuit of Exactness in Quantum Physics. And if you already know a little bit about quantum mechanics, you might find the title a little bit strange, because you might know that quantum mechanics is about probabilities and how can one do exact things about these things. But I'll try to give you a bit of a taste for the grand scheme of things. So the talk is divided in many different sections that are all interwoven, but at the beginning, at least, it's a bit of a personal story because I want to tell you why I got interested in the things that I'm doing today. And I think the start that I had is probably a start that many of you have had, namely looking at the stars, thinking about the universe and everything. One really wonders about many things about the cosmos and everything. And when I was young, so Carl Sagan had this television series, Cosmos. I was really taken by that as a young teenager. So I started wondering about astronomy. And one question really attracted my attention quite particularly. I really like to think about stars and how stars are able to produce light and energy. And in those days, essentially, research was already well advanced in that. There was one figurehead from the 1930s that had really understood how stars produce energy, and his name was Hans Bethe. And this name is going to come back later because it's completely central to much of the story here. But yeah, so I wanted to be an astronomer, and I went to study in Montreal. Indeed, the CV that was presented is entirely accurate, so it's very good. I went to Montreal because I wanted to be an astrophysicist. But after working a little bit in astrophysics, I started getting interested in other things. Today, I'm a professor of condensed matter theory, but starting in astrophysics, I then went to high energy, then I went to optics, then I went more to nonlinear systems and mathematical physics. And up to this day, I have never followed a course in condensed matter theory, although I'm a professor of condensed matter theory. I've tried everything else. But yeah, so I ended up in condensed matter anyway. So that was the beginning. And of course, the important ingredient of the story is quantum mechanics. So I don't know if many of you are familiar with all the basic concepts of quantum mechanics. Essentially, at the end of the 19th century, there was a catastrophe in physics. The catastrophe was that if you had a body at a certain temperature, there should be, according to classical theory, an infinite amount of energy flowing out of that in the form of radiation. And in 1905, Max Planck made a hypothesis to resolve that problem. And that hypothesis was that energy came in so-called quanta, that is, indivisible units that could not be chopped into smaller pieces. And with this quantum hypothesis, the world changed, essentially. Planck himself did not follow through with quantum mechanics. It was his hypothesis. In fact, I think he really resented being the father of the quantum hypothesis. Others took this forward. In particular, in the 1920s, people like Werner Heisenberg and Pascual Jordan, they developed a completely different language to talk about physics. So instead of talking about particles with mass and velocity, they said you should think of matrices, tables of numbers that represent for you the position or the momentum of particles. And the mechanics of these objects is completely different from Newtonian mechanics. In particular, the rules lead to quite baffling conclusions. For example, that you cannot know the position and the velocity of a particle simultaneously. There are these uncertainty relations inherent to quantum mechanics that prevent you from having detailed knowledge of everything you might want to know about a physical system. Then there was a kind of moment of inspiration, purportedly during a weekend skiing somewhere in the Alps, from Erwin Schrödinger, who introduced the notion of a wave function. A wave function is an object that lives everywhere in space, representing for you a state of a physical system. And it evolves in time according to an equation, which is known as the Schrödinger equation. And one of the consequences of that formulation is that reality does not seem to be uniquely defined. It seems like there are multiple, simultaneously present, incompatible situations. And the classic example, which is one of the worst, how could I say, descriptors of anything in physics, is the famous Schrödinger's cat representation. So it's a very evil example here. You have a cat in a box with a flask of poison with a little hammer that has or not fallen onto the poison depending on a certain radioactive particle. Completely concocted. But what you have to keep in mind is that according to quantum mechanics, if you do not interrogate the system, namely if you don't look in the box, you do not know if the cat is still alive or is it dead. And in fact, it is possible to prove experimentally that in order for the predictions of quantum mechanics to be consistent with what we observe, the cat has to be simultaneously alive and dead at the same time because of so-called interference effects and things like that. Of course, it doesn't work with cats. Please don't try that with your cat at home. But with fundamental particles, this is a feature that is inherent to it. In fact, your mobile phones, your computers would not work if the constituent particles of these things did not behave according to this prescription. Okay, so this is very important. Now, the interpretation of quantum mechanics was pushed forward or completed by a contribution from Max Born, who provided the probabilistic interpretation of the meaning of the wave function. So the wave function, which takes its value everywhere in space, it represents the probability, for example, of a particle of being at a certain place. So the predictions of quantum mechanics are inherently probabilistic. They do not tell you that the particle is going to be here. They tell you that if you were to repeat the experiment a certain number of times, then the statistics of the distribution of the results you would obtain obey the laws of quantum mechanics, with the Born rule saying that the probabilities are given by the, if you want, the size of the wave function at that point. Okay, so this is very important. Actually, there are many reasons to like Max Born. If you know Olivia Newton-John, if you're of a certain age, you'll know that he's the grandfather of Olivia Newton-John, but he also won the Physics Nobel Prize. And during his Physics Nobel Prize speech, he said a thing which I think is very beautiful and very important. So he said, "I believe that ideas such as absolute certitude, absolute exactness, final truth are figments of the imagination which should not be admissible in any field of science. On the other hand, any assertion or probability is either right or wrong from the standpoint of the theory on which it is based. This loosening of thinking seems to me to be the greatest blessing which modern science has given to us. For the belief in a single truth and in being the possessor thereof is the root cause of all evil in the world." Words that are still completely relevant today. Quantum mechanics really came forward in the early days of the 20th century with also the contact with atomic physics. So quantum mechanics was tried and tested, polished and perfected, looking at atoms, simple atoms, and how they interact with light. It was observed that there were discrete energy levels to atoms, and there was nothing in between. So electrons would be able to go to certain levels, but not spend any time in between. So the basic model of Bohr at the beginning, predating the real developments of quantum mechanics, was already good enough to explain many of the spectra observed in the lab. And today, essentially, quantum mechanics has been pushed to extremes in the form of understanding of the details, for example, of all the constituent elements that you have around you. You know about the periodic table, all the elements that you can find in nature. The structure of the periodic table is dictated by the basic laws of quantum mechanics. In fact, if you are an arrogant physicist, you say that chemistry has been reduced to applications of quantum mechanics. That's not really true, because we can't really do absolutely everything. The chemists know much better how compounds of things work together. We are not able to calculate all these things today. However, one can say that the foothold of the periodic table is really fundamentally an expression of the basic laws of quantum mechanics. Okay, so that's super important. But of course, that's all done things. So the question is, how far can one go? And I want to discuss a little bit the concept of solvability, what we can actually do and what we cannot do in physics. So you will know a certain number of problems of classical mechanics that are such that we are able to compute exact solutions to these things. So the classic Kepler problem, so two masses linked together by gravity and approximated as, pure spheres. This problem essentially was solved by Newtonian dynamics, and one can find a variety of possible types of orbits of two objects next to each other. The generic form of the orbit is an ellipse, okay? And depending on the initial conditions, you will get different types of orbits. But if you restrict yourself to two bodies, and you simplify these two bodies as if they were point masses, then the mathematics of this is completely under control. One can write down all the possible solutions. Okay, and given initial conditions, one can find the unique solution to this. So that's one exactly solvable problem. Now, there are other approximations that are also solvable. The harmonic oscillator is essentially the workhorse of physicists. The harmonic oscillator, as represented either by a pendulum or perhaps a mass oscillating on a spring, is, there's Hooke's law. You've studied that at secondary school. You get this pure harmonic motion based on certain approximations that are justified in certain limits. For example, in the pendulum, if the pendulum amplitude is not too large, then this harmonic approximation is very accurate, okay? But I will offend my colleagues in telling you that, actually, this is the only system that theoretical physicists are able to solve, except for the Kepler problem, okay? To a first approximation. How complicated can it be? Well, let's say you consider 3 bodies instead, 3 masses. Then, except in exceptional situations with fine-tuned initial conditions, this problem is unsolvable. It's chaotic, namely that small deviations of initial conditions lead at long times to completely unpredictable outcomes. So we have a fundamental wall here. This is known to be unsolvable. It doesn't matter how many computers you throw at this. It doesn't matter how smart you are with your mathematics. This is an unsolvable, chaotic problem. Okay, one cannot deal with this. So that's a bit disappointing. Now, let me look at a completely different system here. So you all have a refrigerator at home. I presume you all have little magnets on the door of your refrigerator. These little magnets are so-called magnetic dipoles, and you will have played with these things. If you bring 2 of them together, they will either repel or attract, depending on the orientation that you give them relative to each other. Atoms, very often, are just like that. In particular, copper atoms, they have a magnetic moment like this, which means that microscopically, they look like little fridge magnets. And in crystals of matter containing these atoms, you have these magnetic moments talking to each other, okay? And in the early days of quantum mechanics, there was a lot of effort to understand how the magnetism inside matter arranged itself. And Heisenberg, in the very early days of quantum mechanics, he wrote a model. So essentially 1 year after the birth of quantum mechanics, he wrote a model, the so-called Heisenberg model, which tells you what is the energy of these magnetic moments when they are close to each other. And this comes in the form of so-called spin chains. So imagine that you have a one-dimensional array of these little magnetic moments. You'll see this is an important thing for later. That's a basic model of quantum mechanics. Now, there's one problem here. It's the problem of many-body physics. We've already seen that 2-body to 3-body in the gravitational case of classical mechanics leads to unsolvable situations. In quantum mechanics, it is very much like that. So if I have a certain number of particles, then the interactions between particles, if the interactions are between pairs of particles, they propagate out. So one can interact with another, that interacts with another, that interacts with another. And very often, this kind of circus of interactions of one particle to another, it doesn't feel like it converges. And we call such a system a strongly correlated system. Namely, if you were to add a new atom onto the set of atoms that you already have, suddenly everybody would need to change a little bit to make space for the new one. It's not like things are smoothly varied from one situation to another. You really have these strong changes because the interactions are really coupling absolutely everybody. So that's a very complicated problem, and in a sense, you could say, time to look for a new career, because I could only do the 2-body problem, 3-body problem's already out. How on earth am I meant to deal with such problems, especially if also it's in quantum mechanics? Okay, so essentially, part of my story is that what is a problem here is also an opportunity. You can say, okay, you are trying to convince us that strongly correlated systems are important. How strong can correlations be? So if I told you that if I took a piece of metal and put little electrodes here and tried to push a current through that piece of metal, if I told you that if there was a single atom, which is a magnetic impurity inside this sample, this single atom could cut the electrical current, you'd be surprised. But this is true. There's an effect called the Kondo effect that comes from the interactions between little magnets in, say, a copper impurity inside an otherwise non-magnetic sample. And when the electrons try to go through, they interact with this little moment. And this single atom there is able to cut the current in this macroscopic sample. So this shows you the strength of these correlations. When a single atom is able to cut conductivity through a macroscopic sample, interactions are very, very strong. So this was understood in the 1950s, led to lots of theoretical developments in the late 20th century. So in particular theory of renormalization and everything, but also exact solutions that I'll be talking about. So that's just an illustration of the existence of situations where strong correlations can completely change the physics, the expected physics, from a basic sample. Okay, so in that case, it was a problem. It cut the conductivity. In other cases, it's a fabulous discovery. So we're in the early part of the 20th century. We're in Leiden, actually, so one of the great laboratories for condensed matter physics. And Heike Kamerlingh-Onnes, I don't think he's a household name in the world, but yeah, so fabulous physicist from back then, Nobel Prize winner as well. And so he came across a phenomenon which was completely unexpected. The experiment for this actually relied on people who were able to do glass structures at an extremely fine level. Okay, so you know glass blowers, people who kind of blow in tubes and make nice bottles, things. So in those days, there were technicians in Leiden able to weave glass tubes into tiny, tiny structures that you see summarized here, in which Kamerlingh-Onnes was able to push mercury. You know, mercury is a metal that is liquid at room temperature. So he was able to push the mercury at room temperature inside these little conducts, then freeze it, and then measure transport of electricity through that. And what he found was completely astounding, because people were arguing about conductivity. What he saw is that at a certain temperature, suddenly there was a transition. Below that temperature, this piece of metal showed no resistance whatsoever to electrical current. And it's not very small, unmeasurable resistance. No, it is an absolutely perfect zero of resistance. And this is a phenomenon that is called superconductivity. So discovery 1911. Many years later, there was another version of this discovered, high temperature superconductivity in different types of crystals. And to this day, the challenge is open. Can we find a crystal, a piece of matter, that displays superconductivity like this, but at room temperature? And if one was able to find such a material, then suddenly electricity supply, as you know it, would be completely transformed. Okay? First of all, we could carry much more of it. We could even keep it, because we could have a nice little ring in which the electricity goes round and round and round and round and round and round until you need it. Okay? But unfortunately, we only have superconductors that are still such that you need very cold temperatures. So you need big refrigerators, so it doesn't quite work yet. But the promise is out there. Is it possible? We're still looking for it. But again, this is an example of complete unpredictability of the phenomena. Camerlingonus was looking for something completely different. They were arguing about essentially the sources of resistivity in these metals, and this was an entirely unexpected result. Okay? So these correlations that you have between the constituents, they also give you opportunities. You can actually come up with things that you hadn't predicted, but that might have very good utility. Okay, so now let's go back in history. We're now in 1931, and Hans Bethe just visited Enrico Fermi in Rome. And so he's a 26-year-old young student, and what he does is he looks at the model of Heisenberg, and he says, I can actually solve the Schrödinger equation for that model exactly. I can just write down the solution, classify all the states. So this is an absolutely humongous achievement that was thereafter ignored for decades, okay? Because nobody knew how to push it forward. But Hans Bethe, the one who discovered the CNO cycle, so energy production in stars, the same person beforehand had done this work. And the way I view this kind of theoretical approach here is that we have this big mess of correlated systems. We have this big impossibility of understanding all these things coming at us with crashing waves, but in some circumstances, we are able to say things in a detailed fashion. Okay, so I view this integrability here as this kind of lighthouse in the storm that we have. And the history underlying all of this also goes back to much earlier. In 1834, in Edinburgh, in Scotland, there was somebody called John Scott Russell, who was a naval engineer. And he observed a very, very strange thing. So there was a canal. There was a barge that suddenly stopped. There was a mass of water that accumulated, and this mass of water just detached and started propagating. Okay, you see the movie, I show you. And the story is that he had his horse with him, and he followed that mass of water for a couple of miles. And he said this was remarkable because it's a single wave, localized in space, that moves without deformation. And you all know that waves are waves. They go up and down and up and down and up and down, okay? The Fourier waves. But this was a solitary wave, okay? So he called that the solitary wave of translation, and it was reproduced. So I think this is like 2005 or something at Heriot-Watt University. They went to the Union Canal again, and they recreated such a wave. So that's how it looks. And you'll understand what the relationship is to what I'm saying in a minute. So the idea is that the mathematics for this was different than the mathematics that was used to solve other problems. There are two people from Amsterdam who are extremely famous for describing the waves in that situation here. They're called Korteweg and de Vries. So they come from my university, the University of Amsterdam. But yeah, of course, what they don't say, it's that Joseph Boussinesq, the Frenchman, had done this a few decades before. So it's really the Boussinesq equation, but because I'm employed by the University of Amsterdam, I'll just still call it the Korteweg-de Vries equation, okay? But my French sympathy is all, you know, I have to. So that was one thing, yeah? So there was this understanding from John Scott Russell that there were these strange things happening. These solitary waves that showed up. Then, again, in a completely different, unrelated development, immediately after the war, they had the first computers at their disposal to do some simple calculations, most of the time for nefarious things, like calculating neutron absorption for nuclear bombs and things like that. But sometimes they did fun physics with this. And then Enrico Fermi, John Pasta, and Stanisław Ulam, they ran a numerical experiment with little particles talking to each other according to some relationships. And they prepared the system in a state where there was, if you want, a solitary wave. And what they saw is that this solitary wave just decayed, and everything thermalized, everything equilibrated. But then, by mistake, they let the computer run longer. And what they saw is that the disorder started reorganizing itself again, and the initial condition came back. So you have to understand how baffling this is. When, if you put milk in your coffee, or perhaps in your tea, you put the milk in the coffee and you stir, then the mixture equilibrates. And if you come back 15 minutes later, it will not be the case that the milk has come back to the top, or, the milk stays mixed. But here, the mixing was undone. So this is the Fermi-Pasta-Ulam paradox. And actually, when the paper came out, Enrico Fermi was already dead. And the tragedy is that the person who actually did the numerical experiments is Mary Tsingu. So she was a computer. She was the person operating the machines. She was the coder developing these things. She's still alive, but her name was not on the paper. So you see how dramatic it was. It was better to be a dead male back then. You had better chances of being on the paper than if you were the female who had actually done the work. Okay, so hopefully things are a little bit better today, but it shows the degree to which things need to change. So this was quite important, actually. And a bit later, in another numerical experiment, now in the early 1960s, so the Fermi-Pasta-Ulam, you're talking end of the 1940s. So you can imagine the computers that they had back then, not very powerful. Now we're at the beginning of the 1960s, and these two mathematicians also run computer experiments on equations that look like the Boussinesq-Korteweg-de Vries equations. And then they see that in those equations, they can have localized waves that stay stable as they move, exactly like John Scott Russell had seen. Okay? And this leads, as far as I'm concerned, to possibly the most beautiful part of mathematical physics of the 20th century. It's a framework that's called the classical inverse scattering method. It's an absolutely beautiful way of thinking about these differential equations that you get in there, and how you can understand the existence of these exact solutions to these things. Okay, so very compelling mathematics in there. Now, the reason why these things work is profound. In physics, one of the most important concepts is the concept of symmetry. Okay? Maybe you have something, well, if you have a perfect profile, you look at yourself in the mirror and the profile is inverted, you look just the same. If you're a bit like me, it's a bit different. There are symmetries in physical systems that are associated to invariance under certain operations. Maybe you take something and you indeed mirror flip it. Maybe you rotate it and it still looks the same. The existence of a symmetry is associated to the existence of what we call a conserved charge. That is, a physical quantity whose value is independent of time. Okay? You've heard, for example, that energy is conserved in systems. So energy is a symmetry. It's a time translational symmetry of a system. The point of these complicated systems is that they have many, many complicated symmetries present. So the beauty of the mathematical framework was to be able to understand all those symmetries. But the depth of the reason why we love symmetry so much, we owe to another woman, Emmy Noether. So through her theorem, Noether's theorem, she linked directly the existence of a symmetry with the existence of a conserved charge. And you might think that this is a constraint, but actually, the existence of these constraints gives you the richness of these physical systems. And for lay people, I really like to compare that to the music of Bach. Bach is a collection of constraints. You fix yourself very, very many constraints. And it is the constraints themselves that give form to the beautiful thing that you have. You think that because you give yourself many constraints, you don't have any movement, you don't have any freedom anymore. Remove the constraints. But no. Out of the constraints come the symmetries. And therefore comes the structure for it all. Okay, so if you want, that's like the philosophical motivation for this whole branch. Now, a few years later, so essentially from the 60s, but mostly 70s up until about 1980, this whole field of, if you want, highly symmetrical system was transcribed to the quantum case. Okay, and there are famous actors. Actually, Zhenyin Yang, 1922, you see, he's still alive. So he's still active in China. Rodney Baxter, also a bit younger, but still alive. Ludwig Fadeev, a Russian person, passed away a few years ago. But these are the people who essentially quantized the whole thing. And if you want to understand why this is such a useful thing, think of this analogy. If we take a model like the Heisenberg model through Hans Bethe's approach and understanding of these things, we can map it to systems that we are able to solve. So here, that's what I mean. A spin chain, you can understand in a certain way in terms of harmonic oscillators that you can know and characterize and which you can use to predict physical characteristics. So does this really exist? Beautiful mathematics, but does it have anything to do with reality? Well, let me try to give you some examples. Perhaps some of you have grown copper sulfate at secondary school. I guess you will have done that. Beautiful blue crystals. You just need a bit of acid, a bit of copper, and then you can actually grow these things. They can be quite large. Amazingly, these are Heisenberg chains. So this three-dimensional crystal you can view really as little one-dimensional chains of atom weakly coupled to each other, as if they were a three-dimensional stack of straws. Okay? So that's a crystal. And there's an artist in the UK, Roger Hjorns, who essentially coated an entire apartment with copper sulfate for an art installation. I tried to contact him and his agent to say, you know, Mister, do you realize that you have the greatest collection of Heisenberg chains in the galaxy? Aren't you interested in our scientific paper here where we do observations on that? And I never heard from him, disappointingly. But anyway, so there you have it, the greatest collection of Heisenberg chains in the known universe. So if you're a scientist, what you find interesting is that this real crystal is genuinely accurately described by the Heisenberg model. And the Heisenberg model is a model for which I can do the theory. Therefore, I can predict what they should see in the experiment. And what is the experiment? It's called neutron scattering. I don't really have the time to explain, but if you want, it's the magnetic version of like X-rays. Here you just throw neutrons, which are little magnets, onto the crystal, and the little magnets interact with the little magnets in the crystal, and they can induce some spin flips, and then the spin waves come out, and we can compute how this neutron gets deflected. So you have correspondence between theory on the right and experiment on the left, and you know, it's all honky-dory, it all works very, very well. And this is using the power of integrability in order to be able to do the computation. And in fact, the instruments of neutron scattering can be calibrated from the detailed knowledge of the theory. Okay, so there are many different areas where other models that are known to display these extended symmetries are applicable. So quantum magnetism, I've just mentioned. There's also the whole field of cold atoms. So these are atoms that are held in space by light fields and that you can gently let interact with each other. You can also do things about that. There are quantum dots. So these are essentially little islands in which you can deposit electrons and try to move them through. Also, the more traditional field of atomic physics, nuclear physics, is amenable to these exact solutions. So in the future, I hope to be able to get back to this. And these are, of course, different models, but the idea is very often the same. So we have these models that have these extended symmetries that allow us to be able to do computations that are otherwise inaccessible if you don't have these mathematical structures to help you. So if I try to summarize for you the history of integrability over the last, say, decade and a half, I like to quote Isaiah Berlin. So when I was in Oxford, I was fortunate to be in a college called All Souls College. And this is the ideal ivory tower for an academic because it only has fellows, okay? Isaiah Berlin was difficult to describe, not really a philosopher, not really a historian. He called himself a conversationalist. So he was very good at talking about many things. And he wrote a series of beautiful essays. One of the essays is about Russian literature, about Tolstoy. And it's based on an old saying by a Greek poet called Archilochus that says, the fox knows many things, but the hedgehog knows one big thing. So the fox is very smart. It can survive in lots of different situations. It's very creative. It's very adaptable. The hedgehog is pretty hopeless because it only knows how to defend itself, but otherwise, not much. So the traditional approach to condensed matter is really based on how the fox does it. So you have general theories that you can invoke, approaches that are amenable to whatever system you're considering, but their lack of constraint and therefore general applicability means also that they're not very good. They give you inaccurate results. They give you uncontrolled approximations. You're not quite sure how it all pans out. But the fox is always able to tell you something. It might be completely wrong, but the fox will tell you something. And on the other hand, the hedgehog, well, the hedgehog knows how to do one thing, which is to write a Bethe-Ansatz wave function like Hans Bethe did in 1931. But then the hedgehog has a few friends, namely the people who did soliton theory, the people who did inverse scattering, the people who did quantum inverse scattering. And then the hedgehog and his friends started to realize that the mathematical structures underlying all these models were unified in a huge framework that was able to explain everything in a kind of grandiose theory. And the hedgehog, although it was only able to do these narrow things, suddenly realized that these models were applicable in very many different fields of physics and were able to give very detailed predictions to real observable things in many of these circumstances. It's not able to do everything, but what it is able to do, it's able to do much better than anything else. Okay? Because it really maximizes the use of the mathematical structures at the heart of these things. So, what's my summary of integrability over the last 15 years? The hedgehog has become a fox. Okay? It's not able to do everything, but it's much more foxy than it used to be. Okay? So that's the recent history. But what about the future? Let me give you, in a short illustration, my hope for the future of the field. So, again, an illustration here. Piotr Kapitsa in 1951 described a mechanical system which is very, very simple. You know the usual oscillator. I don't have a big stick here, but imagine a big stick with a big mass at the bottom. You hold the stick, and you can just have a pendulum from this. Okay? Normal harmonic oscillator. But now, imagine the following experiment. You are holding this rigid stick with a mass at the end, but you start oscillating the suspension point. You start vibrating it. And suddenly, if you vibrate it fast enough, there is a new equilibrium that can show up where the pendulum is inverted. And the pendulum oscillates from the top rather than the bottom. And because I knew you would not trust me, I especially used my metalworking skills to build for you an example of a Kapitsa pendulum. So this is just a mechanical oscillator, and if the frequency of oscillation is rapid enough, you see the thing oscillates upside down. It's not an equilibrium thing. You need to oscillate it. However, it has a new equilibrium that did not exist when you were just looking at the normal things. Okay? So what is this an illustration of? It's an illustration of the fact that if you look around you at all the systems that you have at your disposal, some of those systems, if you knew how to shake them up in the right way, would suddenly have physical properties that you would be interested in. You have to know how to shake them. None of the theories of the fox, of all the foxes out there, are able to even begin to treat systems like that. Super complicated. My hope is that the methods based on integrability and these exact solutions are able to treat at least some representative cases of that. So I would like to, in the future, be able to give you realizations of this. I have got some ideas in here, but it gets technical, and maybe it's best to keep that for, pub discussions later on. But I do hope that these extended symmetries, this beautiful mathematics at the heart of these models, is powerful enough to allow us to go to regions that we are otherwise theoretically unable to describe. Okay? And that's essentially the end of the lecture. So I thank you very much for your attention.
Thank you very much. Are there questions from the audience?
Good evening, Professor. So, as far as I understood from your presentation, we know that most systems are not integrable. They don't have an analytic solution. And your proposal is to, instead of looking for an analytic solution for a very general case, to look at specific cases which we know that are well approximated by some physical systems which we already know how to model. Now, in the case of macroscopic systems, we can always sort of poke them to see what they could be approximated by if we have absolutely no idea sort of where to start with. But I imagine that there can be huge scales, sort of relativistic scales, and quantum scales where we cannot sort of look with our eyes. We'd have to have either very specific measuring devices or where the effects only sort of couple and can be seen at a macroscopic scale. And in order to then create some theoretical models, we'd have to find some other source of inspiration to know where to start. And my question is, do you think that there is some other source of this inspiration where someone could look to in order to have some idea where to start, or do you think this is some sort of, that there is no single place, and that in order to have some more phenomenological model, one just has to come up with it?
So that's a very profound question. Thank you very much. Essentially, you can attack these things using different strategies. So if I put temporarily my mathematician's hat on, then what I'm looking for is a machinery that will generate for me all the models that have certain characteristics. And I can ask for solvability to be one of these characteristics. So, and that's the power of this method that I called quantum integrability, the quantum inverse scattering method. The idea of that is that you essentially declare what your constraints are, what your requirements are. Again, it's the idea of starting with structure, imposing structure, and results flowing out of that. So you require solvability, you require the existence of these symmetries, and through the requirement of these requirements, you find the cases that fulfill this. So you can, in principle, build a catalog of models that have these characteristics. And then afterwards, you can ask yourself, well, did we know all of those? Do I have a way of mapping a certain model to a certain system? Okay? So for example, the Heisenberg model, it's a model for spin chains. So essentially things that are on a lattice and where on each side you have two possible configurations. This can be a model for magnets, but it can also be a model for atoms hopping on a lattice with space for up to one atom on a site. So you see two completely different systems have the same model in the end, depending on the interpretation that you have for these things. So there's this great work of classification at the mathematical level that is done. Then there's a great work of mapping these particular models to various circumstances. So there's a lot of work, a lot of flexibility in that. So I think what the current situation is that we know what we can solve. We know most of the mappings that we can make. And now comes the more complicated question, which models are the right ones? And if I change the model a little bit, do I lose the mathematical structures? Do I lose the power of the mathematical structures? Unfortunately, in most of the physical realizations that you have, this is indeed the case. Then you have to come to approximate theories, where you say, okay, we're going to put our fox costume back on, and we're going to say, well, we've got a bit of experience from working with that particular exactly solvable model, where we see how things pan out when we do the calculation. So if we imagine deforming it this way, then maybe we just deform these results in a certain way. So lots of people are trying to adapt this knowledge to more practical situations. But unfortunately, mathematically, it seems excluded that we will find exact solutions to most of the things that we're interested in. I mentioned superconductivity. Superconductivity, inherently, it's in 2 dimensions, and we know that we do not have 2-dimensional solvable cases like that, and there are profound mathematical reasons why we will never have them. Okay, so it's greatly limited, but the intuition that you get nonetheless from these particular cases does help you in other cases. So yeah, it's a bit of a disappointing answer if you want, but once again, it's a trade-off. You narrow your questions, but then you greatly broaden your answers. I don't know if that answers your question somehow, but your question was much broader than that anyway. But,
All right, any further questions?
You said there are some profound reasons why there are no integrable systems in more than one dimension. Can they be explained, even like the basic idea behind them?
Of course, the easy explanation for me relies on technicalities of the shapes of the solutions to the Schrödinger equation here. Perhaps I can give you a more intuitive explanation here. Let's say that you are living in a one-dimensional world. And perhaps you're doing like traffic on a single lane highway. And there's no way of overtaking. Then there's an interaction between the cars, and this interaction is always going to be maximal somehow. Cars, you know, so it doesn't really matter whether the interaction is a bit longer range or, you know, if you need to get closer. You will have a configuration that will probe the maximal value of the interaction, namely the collision. So this inevitability of the interactions in 1D actually simplifies things, because if you want, the treatment always needs to consider these configurations that maximize, but these are readily accessible. So now contrast it with 2D. So now you're in a big parking lot, or you're in a big playing field, and your particles can keep away from each other, but they can also come very close to each other. So that means that essentially, depending on whether you're looking at low energy processes where nothing comes close, or you're looking at very high energy processes where things really collide onto each other, you get very different styles of physics, very many different types of behavior that is very difficult to capture in a simplified model. So, so if you want, that's the kind of intuitive reason why that's the case. The variety or the range of scales of interactions in 2D is, or in higher D, is much bigger than in 1D. So yeah. But otherwise, yeah, it's about representations of the permutation group in 1D or 2D and things. But yeah, so that's what it means.
Okay, further questions?
Not a question, but a comment. I just wanted to add to what you have shown us about quantum dots, that this could be also used in quantum dots. I would like to mention that it's not only just a mathematical thing, just an example, but this quantum dots are actually used in screens technology nowadays. For now they are used in the, for example, as filters. The screen that we were looking at, I'm not sure if it uses that, but quantum dots can be used to filter the. For example, you have a white backlight. It can filter the frequencies much better than the previous filters, and in the future it could be used to actually emit the light itself. The work is in progress. I just wanted to add that.
I fully concur. So indeed, I don't have the time to give you all the different realizations. So quantum dots are a very, very important part of condensed matter, and it's used. There's interesting electronics going on in there that is also extremely interesting because you have single electrons that end up being coupled to many, many, many particles. So you get creatures showing up in there that rely on the existence of these strong correlations. And again, that opens up the door to very exotic physics in there. So just to, perhaps you've heard the word, the name Duncan Haldane. So Duncan's always been one of my heroes because he's like an extraterrestrial. He's so smart, he's just like in space. But he really nailed the concept of what we call the Luttinger liquid. And this is a new state of matter that exists in one dimension. And the best illustration of this is if you have an electron. An electron, it's a fundamental particle. It has electric charge, minus E. It has magnetic moment also. It has spin half. And these two things, these two degrees of freedom are linked to each other because the electron, as far as we know, is a point particle. Therefore, the charge and the spin, they're in the same place. However, if you have a one-dimensional conductor and you put an electron inside, then what you see are two waves. One wave carrying the electrical charge and one wave carrying the spin. But those waves, they're a bit like John Scott Russell's waves. Those waves, they do not propagate at the same velocity. So really, morally, what's happening is that you inject an electron in such a system, and the system splits the electron in two pieces, one carrying the charge, one carrying the spin. It's because in this world, there is no such thing as an electron. There are only collective waves, okay? And that's an extremely profound concept. That these strong correlations lead to in there. And if we're able to control that, I think we'd be able to build devices that would be like even more magical than the even copper wires we end up using every day. Okay, so and that also is like generalization of what happens in these dots. So yeah, we'll see what the future brings. Yeah.
Are there any more questions? I can't see any, so it means that this is our time to thank the speaker once again.